The next equation from Chapter 6, you've got to know, it's the Rydberg equation. Now, it's important to note, here boldly, you can only use this equation for hydrogen atoms. So that's the big tell. The Rydberg constant, or Rydberg constant, it's a very small number, 10 to the minus 18 joules, and you're tracking the final quantum state, or energy level, minus the initial. So 1 over n squared minus 1 over the initial squared. So that equation you've got to know is for a change in energy, for a transition in a hydrogen atom. So here's a typical Rydberg equation problem. You've got an electron and a hydrogen atom relaxing to the n equals 4 level, emitting light of 114 terahertz. What's the n for the level in which the electron originated? Change in energy is minus r sub h times 1 over nf squared minus 1 over ni squared. So what we have is the electron, it relaxed to the n equals 4 level. So n equals 4, or the n sub f is 4. Okay, relaxes. N sub I, we don't know. Rydberg's constant, we know it's a constant. We don't know what the change in energy is directly, but we know that we've got a frequency of 114 terahertz. Tera is 10 to the 12th. To make that proper scientific notation, that's the frequency. But we do know, if we know the frequency of a photon of light, we can determine the energy wavelength using the equations we've seen earlier in the play positive. So we have the change in energy is equal to h nu. It's Planck's constant. Smaller. Seconds cancel, left in units of joules. If I do that math, I get that energy to be 7.55 times 10 to the negative or minus 20 joules. That's the change in energy. The questions wanting to know is that, well, first it says that the electron and hydrogen atom relaxes to the n equals 4 level. So relaxes. That term means that the electron goes from a higher quantum state to a lower one, relaxes. When that happens, light is emitted. Therefore, this energy the energy of the photon, that's a raw value. The change in energy was negative. Energy went out of the hydrogen atom. So now we have the change in energy. Equal to minus the Rydberg constant. Times 1 we're solving for the initial quantum state, where the electron originated from. So we can combine terms, divide both sides by the Rydberg constant. So we get 0.0346. Okay, I'm dividing both sides by negative 2.18 times 10 to the minus 18. It's equal to 1 over 16. 4 squared is 16 for 1 over the initial state squared. 1/16 is equal to 0.0625. If I subtract 0.0625 from both sides, negative 0.0279 is equal to negative 1 over n sub I squared. Notice the negatives cancel. So in the initial quantum state, it's going to be equal to 1 over 0.0279 square root of that. So remember from your algebra, multiply both sides by n sub I, and divide 1 by this number. Then to get rid of a square, you take the square root of that. If I do that math correctly, the initial quantum state is going to be equal to 6. It makes sense. It's a higher number. As the electron relaxed in the emitted light, went from a higher quantum state 6 to a lower one of 4.